Up next, I would like to call on screen Rahul Agrawal. Rahul has bootstrap projects like Logistics Promise Engine, product listing ads, ranking component, network data management for supply chain, real-time planning for supply chain, and a lot more in Flipkart in the last 10 years. Joining him is Rajesh Kannan. He's passionate about data-intensive applications, distributed systems, and their evolution in the recent decades. Rajesh works in the customer delivery platform and data platforms at Flipkart. Together, they will be talking to us today about scaling and debugging MySQL for greater than 300K QPS, showcasing the journey of setting up clusters, internal variables to achieve it, and recipes to debug issues. Ladies and gentlemen, over to Rahul and Rajesh.
Confirm, am I audible? Okay, yeah, good afternoon, everyone. My name is Rahul Agrawal. I will quickly jump to the agenda here. So basically, in this talk, we are going to talk about two major parts. First part is going to focus on how do we benchmark our DBs and how do we basically optimize our DBs for the required load, which we are targeting here 300K QPS. And then in second part of the session, we are going to discuss the case studies where we will talk about how do we debug the issues at that kind of QPS. So from the context perspective, right, Flipkart has its own data centers. We do not use any of the public clouds, and we have our own two data centers, one in Hyderabad and one in Chennai. And MySQL is very, very widely used in Flipkart across at least our BU, which is Fulfillment Services Group. We have at least 150 MySQL clusters, and every cluster is having a minimum of 3 nodes, one master, one hot standby, one read replica. These clusters are generally in the range of, from core perspective, 2 to 44 cores. From memory perspective, they are like 8 GB to 244 GB RAM. From disk perspective, they are from 128 GB to 3 TB disk. Right? Here, the case study which we are going to focus on is on the bare metal machines, where we two of our clusters are running on bare metal machines, which has 96 core, 500 GB RAM, and 3 TB disk. So, how do we scale MySQL generally? Right, that's the first comes to our mind. So, beyond the point, if we want to scale MySQL either with respect to data persistence or with respect to throughput requirement, right, we follow one of these strategies. Either we throw more hardware, which is vertical scaling, or we basically go for horizontal scaling, where either you do application level sharding, you go for distributed SQL kind of use cases, which is either TIDB, Yoga by DB, or you use some enterprise solutions like MySQL Calendar. Or in some cases, you also adopt these strategies like horse to worms to kind of strategies to handle the data growth. But in this talk, we are not going to focus on horizontal scaling. We are only going to focus on vertical scaling part, and we will go through some case studies related to that. So why vertical scaling, right? That is the next natural question comes to our mind. That why are we talking about vertical scaling in this era, right? In this era, everybody is talking about horizontal scaling. So the use case where we had to do vertical scaling was because of these legacy systems which we had in Flipkart. These legacy systems are like more than 7 or 8 years old, and they are kind of monolithic applications, which we are already in progress to basically doing the architecture, and hence they are in deprecation mode. But for that period where they are in deprecation mode, we still has to support the sealed QPS requirements, which are almost 5 to 10x of our load during the area. Right? So because of these reasons, and particularly ROI also, right, where we are saying that, okay, why can't I do sharding in my existing system? Because it was very, very complex the way these systems were modeled. Hence, from the ROI perspective also, we thought of doing vertical scaling and investing time in that. So one of the important requirement before we even start the entire supporting 300K QPS, right, was the benchmarking of our workload itself. And to do the benchmarking, one of the strategies generally people use is where you basically benchmark your APIs, right? And generally there are a lot of tools available to benchmark your APIs where you can mimic the similar kind of load of APIs, similar workloads, similar workloads of the API, and then finally you basically benchmark your DBs also, right? But here, the strategy which we took was to benchmark DB independently in production without the involvement of APIs. And for that, we basically built an internal tool, log replay tool. And for monitoring, we were relying on Percona monitoring and management tool, which is again open source. So the next question which really comes to our mind is why we are doing this benchmarking in production, right? Because it was very difficult for us to mimic the production kind of load in any other environment. Because as I told, the second strategy is to do the benchmarking based on APIs. And given that these are very, very old system, monolithic system, there were so many APIs exposed on top of it, there were so many domain entities involved, it was very, very difficult to do the coverage of all the APIs in production if you want to rely on the API level benchmarking. And second problem was that you had to bootstrap your data with similar kind of disk footprint. As I'm talking about the 3 TB kind of footprint, if I'm doing it somewhere else, some other environment, we had to bootstrap that similar kind of data so that we can mimic the same kind of mixed load requirement which we had. So I talked about this log replay tool, right? So what we generally do is we have this kind of topology where we have a master, we have hot standby, slave 1, slave 2, and then slave 3. So this slave 3 we attach behind slave 2 just for the purpose of benchmarking. So what we do is, before we start the benchmarking, we first capture the general logs on our master machine. And these generally it is not recommended to switch on your general logs in production, but just to collect the data from master, what we do is we enable general log for a window, and we stop this replication from master to one of the slave. So in this case, master to slave 2, we will stop the replication, and at the same time we will start a general log. Why we are doing that? Because we want, when we will rerun these general logs on this slave machine, at that time you will not have so many errors that okay, these entities are already in particular state, so kind of things, right? So that is why we stop the replication and we enable the general log. And after that, what we do is we SCP this general log file to a separate host, and from there we use this tool called MySQL Slab to rerun these general logs from this host to slave 2. And what is the purpose of adding slave 3 behind slave 2? During this benchmarking, we also want to observe that is there any replication lag happening on slave 3 or not, because that is also one of the important aspects, that when let's say we will get a sale kind of load, during that event it should not happen that your slaves are lagging just to catch up with your write or read write throughput basically. So what is MySQL Slab? MySQL Slab is an open source provided by MySQL itself, and we created a wrapper on top of it, and then internally we use the MySQL Slab provided capabilities. So some of the features of log replay tool, we basically had transaction support, where let's say what we used to do was this general log file we used to divide into smaller files based on thread ID, and then we used to replay them. So that is how we build the transaction support. Custom playback speed, where you can tune the speed at which you want to hit this slave 2 from this separate host, so that you can tune. Checkpointing for fast resume. So basically, if let's say you are running a benchmarking, and then in between the benchmarking failed, you can actually resume from the same point instead of you capturing the general log again and then rerunning the entire general log. Keyword filter, where if you want to only benchmark for let's say either only reads or updates, that also you can do. So this log replay tool, as I told, internally uses MySQL Slab, and this is just a sample command which you can where you can give an input of query.sql, and you can provide the concurrency iterations, and you can run this command to replay the general log file from this host to slave 2. So this is about basically how do you benchmark. But during benchmarking, we observed and we had to do so much of tuning, right? So first of all, as I said, for the observability part, we are using Percona monitoring toolkit, and that also comes as open source software. So all these graphs are from Percona monitoring graph. So one of the things which we observed during the benchmarking was that okay, our InnoDB log file size, which is generally size of redo log, a journal of recent changes which MySQL maintains, this log file size was very less. So as you can see here, it is only 2 GB. Total size of InnoDB log file size 2 GB, while the data we are writing is 23 GB per hour. So here the thing was, because of that, what was happening was there was a lot of flush activity happening, and hence there was a lot of disk IO which was happening, and that was kind of causing the throughput, that was reducing the overall throughput. And hence generally the recommendation here is that there should be enough redo log space to handle more than an hour of write activity. That is recommended. Hence, in our case, using this graph, we basically visualize that okay, if we change this value from 2 to 12, and what happens is there is a variable called InnoDB log files in group, which if you mention as 2, it means it will maintain 2 files of 12 GB each. So 2 is the default value, and hence overall it will take 24 GB. So now what will happen is this flush activity will happen only once an hour. So that way you will reduce the you will basically save on the disk time. So that is one of the learnings we had during the benchmarking. The second learning was where one of the symptoms we saw during benchmarking was selects were taking a lot of time. And then we started observing, we started basically again looking at some of the graphs, and we figured out that, okay, number of open tables. So there is a variable called table open cache, which basically define number of open tables for all the threads. So why do we need to basically generally keep this value to a certain number? To increase the performance of select queries. So what is the recommendation generally in this case? If you see the value of open tables, which you can see either by running this command, or you can see in PPM graph also, which is there on the next slide. So in this slide, if you will see, number of open tables here are 16.11k, and initially our table open cache was only 8,000. So this was a clear indication for us that we had to increase the table open cache value to 16.19. So that is where we changed this value from 8,000 to 16.19. There is one more variable called table open cache instances. What it does is it basically divide your overall table open cache into smaller instances to reduce the contention among sessions. So in our case, we changed this value from 1 to 8 to given that our workload was there was too much of there were multiple sessions, there was like too much of parameters, hence we had to increase this 1 to 8. Innovative buffer size is a very well-known variable where generally it is recommended to keep it 50 to 7% of overall memory, and this generally helps you cache the data in innovative buffer. The second symptom which we saw was that instead for taking a lot of time during benchmarking, and that is where we started debugging, and we found out that okay, there are these 4 variables which which require tuning. So first variable is InnoDB read IO thread and write IO thread, where the number of IO threads for write operations or read operations in DB. This is what it signifies. Generally, if you can see that okay, if you have so I think this is also mentioned here. So if you will see there is if you run this command show engine in InnoDB status, and if you see that okay, insert buffer size is like a bigger value. In our case, I said 1229. It means there are 1229 unapplied changes, and hence we can consider InnoDB IO capacity. So okay, that was for InnoDB IO capacity. The InnoDB read IO thread, generally you can just see the value of pending read request in show engine InnoDB status, and based on that, if you can see that value is more than 64 cross InnoDB read IO thread, then you can choose to increase these values. So InnoDB IO capacity we increased from 4,000 to 15,000. This I covered in this diagram. Then there is InnoDB auto ink lock mode. So InnoDB auto ink lock mode basically talks about it is basically a lock mode to use for generating auto increment values. So if you are using an auto increment column and you have a high throughput kind of workload, then generally it is recommended to set it to 2 for bin log format equal to row, because in that case it doesn't take any table level auto ink lot. But the only cache here, when you set it to 2, the increment IDs will be monotonically increasing, but they might not be consecutive. That is the only cache. But in our case, this was fine for us, so we went ahead with it. So after doing all these tunings, you can see that okay, we were able to achieve the 300k QPS as shown in this graph. So there is one more angle here that sometimes you might need to optimize on your OS level variables, and you might need to tune that. So one of them is let's say network bandwidth. So in our data center, generally the bandwidth which is available to us is 5 times memory of machine. So if your memory is like 500 GB, then you will be having 2.5 GB, 2.5 GB, 2.5 Gbps bandwidth available. So in this case, if you will see in this graph, this is our utilization was well beyond limit. So this was not an issue for us. Then second thing is disk read and write IOPS, where generally in our data center, 100 IOPS per GB disk is what is available to us. So if we have a 3 TB disk, then it means we have a 3 lakh read IOPS and 3 lakh write IOPS available. So in this case, if you will see, these graphs are showing you how much IOPS we are getting. As of now, we are getting 18.9K read IOPS and 4.4K write IOPS. So what we saw was that, okay, even though 3 lakh we can actually get 3 lakh, but but we were only able to get this much 4.4K and 18.9K. So what we did was we were suspecting that there is a problem with our hard disk, and hence we ran a FIO test on the hard disk, and the output of FIO test, where as you can see the utilization was 100%, but actually read and write ops was very less, like 45K and 5K. So here as you can see, even though my upper cap was 3 lakh, but I was able to get only 50K as a cumulative disk IOPS. So that was an indication for us that even our hardware has actually kind of not working properly, and hence we had to replace the hard disk. So Rajesh Rajesh to continue with the case please.
Thank you, Rahul. I hope I'm audible too. Yes. Yeah. like Rahul, different parameters and which we can use it for tuning and all, right? And many times what will happen is that whenever running systems at scale and maybe for any databases, right? What will happen is that you will encounter various kinds of issues and you don't even know what is the root cause for this issue, right? What is happening? And since we don't have very good understanding on the actual issue itself, right? Uh, you may not know the exact parameters to tune also. And we have faced this similar kind of issues in Flipkart as well. And here I'm going to share our learnings there and how we tackle those problems and all. I will be discussing uh, basically two case studies here, and I will talk about the challenges I mentioned there. And let's go to the first case study. And in this first use case, right, I'm talking about the database which has 20 core CPU, 1.5 TB SSD, and 90 GB RAM. We're using master slave topology. On the QPS point of view, it takes 40K on normal day. On sale day, it is taking around 100K QPS. On this particular sale day, right, we got APIs for taking a lot of time. And after we analyzed, we found that there is some performance issues with our database. And finally, we got this graph. uh, if you can see in this graph, right? Yeah, it's showing the CPU usage of that particular database server, and here I already highlighted that system CPU, and it mentioned around 59 percentage, right? So what it says is that the system CPU part it is taking more on this particular day, which is caused the slowness in our database. And then we took some time to understand what it means also. And basically in Linux, there are two CPU modes are available. It's called user CPU and system CPU. And user CPU talks about the work done in user space and mostly done by the application code. On the other hand, system CPU talks about the work done in the kernel space by the kernel code. And typically it takes less than 10% on the steady state. So now we talked about the different CPU modes, right? So natural question comes like, then when do we go from one mode to another mode, right? And that's where there's something called system call comes into picture. So whenever you make any system call, that's when the control changes from this users mode to the kernel mode. And there are causes for this high CPU could be either you have too many threads competing to run in the system, or you have threads and which they try to enter into some critical sections to access some common data. So after we encounter this issue, we run this command called show engine inability status, which already Rahul covered earlier. This command we will run it inside that MySQL console, and this is the first level tool we use to introspect any MySQL performance. Also, it captures metrics like buffer pool, IO thread, and other performance also, and it also shows different transactions, different queries, and if you can see in this screenshot, right? I actually mentioned one transaction here, and initially it talks about what are the logs it's currently holding, table log and record log. In the below also it is talking about the log it is currently waiting also. So this is what you get it generally, and we used to record this data periodically, and we will check it for historical analysis also in later point in time. On this particular day when we got this issue, right, we ran the same output command. This is the output we got it. Basically we saw all the queries were, but the queries were not waiting for any logs or something like that. All of them were simple queries, but they were already optimized, right? So we did not have any clue on the MySQL side. So now we went to that debugging on that. Now we went to debugging on that MySQL process side, and in MySQL process, right? There is a command available called ptpmp. This is a Perconos profiler command. It basically runs on GDB, and it generates thread stack traces for the given MySQL process, and it also aggregates view by similar traces as well. So this is the output we got it from the ptpmp command, and it shows multiple lines, right? Each line represents it represents the call stack of the similar threads, and the first column talks about the number of threads who has the same call stack, and second section talks about the call stack itself. And here I highlighted that 2 and 3, right? Basically, high level, what you can see is that it talks about maybe TZ, time zone, conversion, GMT, right? What we could get it from this output at the high level. Here I actually paste that single call stack for the closer look and all. I actually highlighted a few methods here, like a lock wait pivot, design, and we will discuss slides. Basically, you can see two section of output here: the work done at that MySQL layer and the work done in that Linux kernel layer also. let's see one at a time. So if you see the track trace belong to the kernel side, right? We found something like lock wait private. When we read about that, we found this is part of the glib library, and it used to make a futex system call, and this futex system call used for low-level locking primitive. It means whenever writing any multi-threaded applications, right? We will use this system call only for the coordination and all. So for what we understood is that we got a lot of MySQL threads and they try to lock some shared data, which is causing this CPU usage for us. On the other hand, if you see the track trace belong to the MySQL side, right? And I mentioned that method name here, which I found there, time zone system dot GMT seconds to time. So high level talks about timestamp and time zone. So this is when we took some time to understand about timestamp data type also, and it is different from datetime data type in MySQL. And these timestamp fields are stored in GMT or the UTC at rest. So whenever we do any read and writing rows, right, we will talk to the maybe we will convert into the local time zone accordingly and return to the end users. This is how it works. Now let's see that different time zone settings provided in MySQL also. So MySQL provides two variables for time zone, two values like system and fixed value. System means the MySQL relies on voice utility for the convention. So it picks that default time zone from that voice preferences only. And in case of fixed values, we can give any hard-coded values like 530 or something like that. In this case, all the conversion happens at the MySQL layer itself. So far, what we concluded is that we are using timestamp heavily in our applications, and when we read or write records, it's talking to Linux utility for the time zone conversion, and the Linux utility is which is making the system call and causing the system CPU problem for us. So now the one part is not clear is that why that Linux utility when it does time zone conversion goes into that locking mode. That's the one it's not very clear so far. So after analysis, we found that this seems to be a known bug in Linux where whenever you do time zone conversion at a high concurrency, right, it is going to some log contention also. It is elevating of the system CPU level also there. And this is faced in many open source databases also like Impala. And this is the respective code snippet I could find on the Linux glibc internal library. So here, if you can see high level, right? I highlighted two lines here. It talks about something like the time zone set lock, and initially we are locking the data structure, and we are doing some work, and finally we are unlocking it, right? And so basically, this data structure is used to protect time zone settings. So high level, what it looks like that basically whenever you do time zone convert, right? That particular code path also using the same code path which is used by the time zone settings change itself. So it needs that this global lock for all the conversions. This is a kind of unwanted behavior in our case. So this is what happened finally. And MySQL, which uses voice utility, and the voice utility takes locks to do time zone conversion, right? Which is the problem for our system from scaling up. So now we talked about the problem, right? Now we got two options. Either we can go to datetime data type. In this case, we don't even go to time zone, right? So no need to do any conversion also. The second option is that we can change the times voice MySQL config to use that fixed value like 530. In this case also, we are avoiding that voice interaction completely. And in our use case, we felt that option number two is more comfortable, and we because of the regression and other things and all, and we chose this. So after you have done this voice change, right? This is the output we got it. So you can see the yellow area. It talks about the system CPU used from the system. After we have done the config change, right? You can see a very major drop here. After that, system backs to normal, and system was also scaling to higher QPS also. Finally, it was a good experience for us. And now let's go to our second case study. And in this case, right, we have another database server there. We saw regular spikes in our DB load average also. And it causes latency in our application sites frequently. I highlighted them in this spikes graph. So like we said, right, we run that DB status command again here. Here also we could not find any transition waiting for lock and all, but we saw something like some of here. Semaphore is the first section, transaction is the second section. Under semaphore, you can see that some thread with so and so number has waited for some lock, which is particular source code line in MySQL. It talks about where this lock is created in another file location. It also mentions that the corresponding Percona build number location also. In the bottom, you can see that a transaction is running a query and it has its one thread reference also, right? And the same thread is mentioned in that semaphore section also. So high level, what we can conclude is that our queries were taking longer time and their queries were not waiting for any transaction logs, but they were internally waiting for some kind of semaphores as per the above section. Yeah, to understand more, right? Let's understand some basics from MySQL also. MySQL has various data structures like buffer pool, B-tree pages, and different buffers like change, log, and double write. And it also has many threads for different purposes. There are something called connection threads, and one for each DB connections, and it used for all the query handling and all. And it also has many internal threads used for IO, buffer pool, and other activities. So now we saw the different data structures and thread, right? So that's where the semaphore has a place there. So whenever we want to protect an internal data structures from concurrent access by multiple threads, we go for semaphores. They are called latches and mutexes, and generally they are taken for a very short period of time. And since we talked about the source code references in our screenshot, we have analyzed the respective source code with the same build here. This is the respective source we could find it from that internet. So I highlighted the documentation here. It talks about creates and initializes the adaptive search system at database start. So we took some time to understand what it does also. We also read the various online blogs. This is what we understood finally. And there is something called adaptive hash indexing or AHI, which I will talk about here. Before diving in, right, let's talk about how data is stored in MySQL also. And in MySQL, data are stored in that B-tree leaf pages. So for any lookup, we'll always iterate from the root node and we'll all the way to the leaf node we have to go, right? So that root to leaf node is taking a lot of time and it is generally costly. So to solve this problem, right, MySQL builds a cache table called adaptive hash indexes and it caches that records directly. So this cache is available and this is the global data structures. It means that whenever you read or write any records or whenever you want to update this table, right, you have to take the respective logs also. So what could be the potential impact is that when there are too many threads reading or updating the rows, right, this causes AHI to have a lot of contention also. So now we talked about what is AHI and what's the importance. We talked about its pitfalls also, right? Now the question naturally will come like, and why are we using adaptive hash indexes or when do we use it? When do we help us, right? And since it acts like a cache layer to access the records directly. So what we can say is that if the cache misses less than 10 percentage or you don't see any threads containing for logs in that semaphore section, right? Then we can very well say is that this AHI is helping us. But in our particular use case in this scenario, I mentioned that AHI miss ratio here. So here you can see that this value on average is 20%. On those peak times, it goes up to 50% also. So it surely says this particular setting did not help us. So as a solution, we went ahead and disabled that AHI setting via this particular value. After that, right, we saw that load average dropped, very well. It also back to normal. It also scaled very well. Yeah, thank you. And let's go to that.